We're about to look at properties of the derivative of a vector value. Oh, I guess you must remember these properties from Calculus 1. Note, most of them were in Calculus 1, but the format is a little different. So if we assume R and U are vector valued functions, and f of t is a scalar function, there's nothing special here you don't already know. Just be careful to distinguish vector answers from scalar answers. Okay, first of all, the derivative of a constant times a vector valued function is that constant times the derivative of the vector valued function, which is just as you would expect. The derivative of the sum of two vector valued functions is the sum of the derivatives of those two vector valued functions, which is also exactly what you'd expect. Now this is interesting. This is a scalar function times a vector valued function, and the derivative of that product is the scalar function times the derivative of the vector valued function plus the derivative of the scalar function times the vector valued function. So that's a scalar product, but nonetheless the product rule holds. This one is interesting. We have the derivative of the dot product of two vector valued functions, and again the product rule holds. First times the derivative of the second plus derivative of the first times the second, or second times the derivative of the first, whichever way you want to look at it. First d second plus second d first. You've probably heard that before. And interesting to note that the derivative of a dot product, remember the dot product of two vector valued functions will give us a scalar function, and so this derivative on this side as well as this side will be a scalar. Now the cross product of two vectors, if you took the derivative of that, then it's the first cross the derivative of the second plus the derivative of the first cross the second. So again, it's the product rule, but it's interesting that the result of this differentiation will give us the sum of two cross products, which is itself a vector plus a vector, which is another vector. Now, if we have a vector valued function evaluated not at t but at some f of t, and we want the derivative of that, then it's the derivative of the vector valued function evaluated at f of t, but then from the chain rule times the derivative of the inside function. So the chain rule applies to vector valued functions. Also, this might be new. If the dot product of two vector valued functions is constant, then the vector valued function times its derivative is equal to 0. That's not times, that should be dot. And now that's interesting. What do you know about the dot product of vectors? Well, the dot product of vectors equals 0 means the vectors are orthogonal. So why would that be? And I would think of it like this. If the dot product of two vectors is c, then the length of that, sorry, that's not two vectors, dot product of the vector with the self is c, then the length of that vector is constant. Well, if the length of that vector is constant, then it's something that's turning around in a circle. And so if you looked at the way in an instant going around in a circle, the vector valued function coming inward, the vector valued derivative is instantaneous going outward, and so you could see that those two vectors would be orthogonal.